Hello everyone. In last lecture we are discussing about design of weld subjected to combined stresses, or you can say design of welds subjected to combined loads. So, there we have already observed what is shear flow, what is allowable shear flow. The detailed concept about those things I have already discussed. Today I will start from the how to find out, you can say, resultant shear flow first. After that, actually I will show you for different loading case how to find resultant shear flow. After that, we will solve one or two problems on weld design based on this concept of shear flow. So, this is the content of today's lecture. First of all, I will discuss about resultant shear flow for different combination of loading case. Then also I will solve some problems on shear flow. It can be one or two problems. So, in last lecture itself I told you that shear flow in x, y and z direction, if it is q x, small q x, q y and q z, then what we can do, the resultant shear flow we can find out by the procedure which is similar to finding out the magnitude of a force when the values of x, y, z direction are known. That is why here I have already discussed this thing, that q r is equal to a square root of q x square plus q y square plus q z square, where q r is equal to, I have already told you, resultant shear flow. You can see here, I have already discussed in detail in last lecture itself. Today I will discuss how this resultant shear flow is calculated for different types of loading conditions. So, first case I will discuss, once a welded structure or once a welded joints subjected to Px and Mz, then how to find out the shear flow, resultant shear flow, you can say, for this case. So, Px and Mz, which is showing here, you can say in figure number 2, you can see. So, I have already told you what is x direction. X direction is perpendicular to the weld surface direction, and you see y and z direction is along the plane of the welds, that I have already discussed. So, this axis system already in last lecture I have discussed. So, this is perpendicular to the weld plane x axis, and y and z is along the plane of weld. What I am telling, understand? Now, if a weld, or you can see if a system of weld is subjected to a load Px, then you know, then this weld will subjected to a shear flow due to Px. This Px already you know, this Px will be generally you can say the force, total force, actually you can say total force acting in x axis, along the x axis. This can be positive or negative. Positive means if it is along the direction of x, if it is opposite to the direction of x, then it will be negative. Okay. Now, Px, if it is subjected, then we know corresponding to the Px there will be a Qx value. Let us consider that I am representing Qx, which is due to Px. I am writing, let us. So, this you can write as force Px along x direction divided by what? Length of the weld, because I have already discussed what is shear flow. Shear flow is shear stress into T. Q is equal to, I have already discussed, shear stress into T. So, shear stress already is very well known to you, and into T is the throat thickness. So, due to this force, that means you can say from here we have already shown this is equivalent to P divided by force divided by, you can say, length of weld, LW equal to length of weld. How it is coming? Because you can see this tau you can write as force divided by total weld area. So, total weld area you can write as P divided by, so tau you can write as P by total weld area. So, this total weld area you can write as length of weld into throat thickness. I have already told you generally along throat thickness shear failure is taken place, that is why always we generally used to consider throat cross sectional area for our design. Okay. So, from here you can easily find out what is Q x due to P x, that is actually P x by L w. How it is coming? Because Q is equal to actually tau into T. So, this T T will be cancelled out, that is why there will be only L w. So, this is Q x due to direct force P x. Now, apart from these things, here you see there is acting a bending moment, that is m z you can say, which is you can see which is generally towards the direction of z. So, based on you can say based on right hand thumb rule, if you what should be, if it will be towards positive direction of z, then your bending moment will be clockwise, then your bending moment will be clockwise direction, and its direction of the bending moment will be towards the positive direction of z. You see, you rotate this way, it will be clockwise direction towards the z direction. So, due to this bending moment, generally in weld, how the bending stress will come? Already you know, because if a beam is subjected to bending moment, then you can see, let us consider this is a beam. If it is subjected to a bending moment, let us consider this bending moment, then you know, let this m is the bending moment, then you know these things, it will bend like this, it will bend like this. This is you can say sagging types of bending moment, you know this thing, sagging types of bending moment. Here top fiber or top side layer is subjected to compression, and this bottom side layer is subjected to you can say tension. So, if you take a section, let us see this section is a square section or whatever rectangular section, then in this section how the bending moment or bending stress will be looks like. So, here the bending stress will be negative maximum at the top, and it is generally 0 at the neutral axis, and at bottom side it will be positive. This is called generally neutral axis. You know this thing very well. So, you see your maximum bending stress is coming, you can say at outer fiber or outer layer of this cross section, and it is generally 0 at the neutral axis or centroidal axis you can say. So, you know this is generally sigma b max you can say, correct. Now, I have already discussed these things, that this sigma b is dependent on what? Bending moment m b y divided by I. This I have already discussed. So, in this case this bending stress will be due to second moment of inertia about z axis. This you should keep, and m b also acting about bending moment also acting about z axis. This you should keep it in mind. Okay. Now, here one things you can observe, that here generally always you should keep it in mind, here z w is, I am just representing these things, I z z divided by y later on I. So, this you can write as like this. So, sigma b is equal to m b by I z z by y. So, here whatever the z w here you are seeing, so you know z w is equal to, always you should keep it in mind. I have already told you generally shear flow Q is equal to stress into throat thickness, clear. So, here whatever the z w is showing, this ZW should be always, you should keep it in mind, that will be here IZZ divided by Y. Here Y should be your outer distance from neutral axis, maximum distance from neutral axis. So, ZW will be IZZ divided by Y divided by T. This you should keep it in mind, because generally Q is sigma into T. So, with this generally if you just multiply here, generally if here in this sigma b, if we multiply T, what are the things you will get? MB into Y into T divided by IZZ is coming, correct. So, this T if you just bring down, so what should be the things? MB divided by IZZ, and this YT will be coming down, YT will be just coming down. This you should keep it in mind. So, IZZ divided by YT is known as, always you should keep it ZW. Okay. So, here MB divided by ZW. So, what is ZW? I have given you the idea. ZW is equal to IZZ divided by Y into T. What is Y? Y is the, you see, Y is the furthest distance from this Z axis, because where the bending stress is maximum, and this bending stress also acting along the direction of, this bending stress also acting along the direction of what? X. You can see here, because you see if this is rotating like this, then how the bending stress will be. So, top fiber you see, that means along Y axis, top fiber along Y direction you can see, will be maximum will be at further distance and minimum will be at neutral axis. After that other direction also, one side will be in compression, here you can see this arrow is downward and other side is tension, so the arrow is upward I have given. You can see here in this figure 2 itself, you can see this is tensile due to this clockwise bending moment, this right side bending stress is tensile, and this left side bending stress I have shown in downward direction, which is negative. This you should come, or compressive in nature, this you should keep it in mind. Now, for finding out resultant Q x due to the combination of, you can say Px and this Mb or Mz, you can say here, you need to add which shear flow component, you need to add shear flow component which is acting along the direction of x only. This you should keep it. So, here Qx resultant, if you go for finding out, this will be equal to due to direct force, you can say here I am writing this I am writing like Qx due to Px plus this will be due to Qx due to Mz. This you should keep it in mind. Okay. So, if you just do it, so always we should consider the maximum value of this Qx, and you should choose that location where this Qx due to Px and Qx due to Mz which is adding. What I am telling, understand? You should choose a location, because you need to find out Qx resultant which is maximum due to this combined force. This you should keep it in mind, because for finding out the resultant allowable, for finding out the allowable types of, you can say shear flow, or you can say resultant shear flow, you need to choose the critical location where your shear flow is maximum. So, that is why you see in this case, you see one side it is compressive in nature, another side it is tensile in nature. So, but here you see due to this Px which is tensile, Px direction, that is why what happens, whatever the location where here we need to choose, that location should be, always you should keep it in mind, due to Mz, that bending stress location you should choose where bending stress is maximum and it is positive in nature. In another case also you can say, if Px is negative, then you need to choose that location for bending stress where bending stress is compressive and its magnitude is maximum. What I am telling, understand? But that means when you add these two effects together, it should give you a maximum shear flow. This you should keep it in mind. Okay. So, we should choose that location where you will get maximum shear flow. Okay. That is why you see. So, here as this we consider Px and Mz both are positive. So, this Qx due to Px will be positive. So, this you can write as Px by Lw, and due to this Mz which is clockwise in nature, this is creating maximum positive bending stress where you see at the outer layer in right side of this section of the weld. This you can see. That is why you see that I am writing Mz divided by, you can say, Zw. So, what is Zw? That things also I have told you. So, how to find out Qx resultant due to the combination of Qx force, Px force and Mz bending moment, this idea you got. So, this is one concept you got. So, these things generally we will add in this equation. This is equation number, let us 7 number of equation, actually last lecture I told you. So, if you put here, you see this Qx, this is actually Qx resultant, you can say this Qx resultant component which will be a squaring. That is why this Px by Lw plus Mz by Zw, if it is tensile in nature, then here it will be positive. If both the things will be compressive in nature, then here will be negative. So, this plus minus sign, once it will be squared, then what happens? It will its magnitude, that sign it will not affect in this QR value, resultant QR value. This you should keep it in mind. That is why I have already written here. Since Qx is squared in the equation number 7, you can say the sign that denotes tension or compression usually deleted. This you should keep it in mind. So, we have already got the idea how to find out Qx shear flow along along x direction, shear flow along x direction Qx resultant I have written. Why Qx resultant? Because this is developing due to the combined effect of direct force Px and moment along z axis, that means Mz, and how it is coming, this I am showing. And this Izz always you should keep it in mind, Izz equal to your overall second moment of area or overall moment of inertia of all welds. So, you should keep it in mind, it is moment of inertia of all welds, whatever the welds will be there in this location, that welds you need to consider, always you should keep it in mind. Now, this is Qx resultant you got. Now, how to find out Qy resultant, Qz resultant, that also you need to know. So, for finding out these things, here what we consider, let us consider a rectangular cross section weld. You see, this is the weld line, and this is the fillet thickness or throat thickness, you can say, at the periphery of this rectangle, you can say. So, here if it is subjected to a torsional types of moment, or you can say torque, this torque generally, you know, this torque is always acting how? Always acting generally, you see, it is acting generally along the direction of the component, and it is generally, you see, it is always acting perpendicular to the direction of weld, because if here the welding is there, if here we do the welding, this is base generally, this is the weld, then generally it is always act perpendicular to the direction of, you see, perpendicular to the direction of weld plane. So, here the perpendicular direction is what? X direction, That is why here you see we need to consider mx. So, this mx is also known as torsional moment or torque. This you should keep it in mind. I have already discussed these things very clearly in last few lectures. So, there you got the idea. So, if a structure welded structure, let us consider a rectangular rectangular side weld and its throat thickness is T, and if it is subjected to a what it is called torsional moment mx, then what should be its what it is called shear flow due to this mx. Generally here one thing you should keep it in mind, due to the torsional effect, the torsional shear stress is maximum where the distance from the centroid of the weld, always you should keep it in mind. This is the CG I am showing, this CG is equal to your centroid of welds. What I am telling, understand? Here if it is a rectangle, then what happened, it should pass the mid length of the, it should pass at, you can say, mid length cross point of this rectangle. This you should keep it in mind, CG. Generally due to this torsional moment, the maximum shear stress will come where? The maximum shear stress will come at the farthest distance from the centroid. So, you see for this rectangle, generally let us consider this is your AE's height and let this is our, I am considering this is our breadth. Okay. So, let us consider AEC is greater than B. So, in this case always you should keep it in mind, here generally your maximum shear stress due to torsion will act at this further corner point, and what happens, it will act perpendicular to the direction of, or you can say it will act perpendicular to the you can say, let this is our centroid is O and this is our A point. So, this should act perpendicular to the line of OA, and it is, its direction will be depends on what? Direction of mx. As here I have shown, as the mx is anticlockwise, that is why at A location this shear stress will act, you see shear stress will act this direction, and it should be perpendicular to, you see this angle should be perpendicular to OA. Similarly, in this corner point also there will be a shear stress. So, throughout the entire corner point you can say for this rectangular case, you see this corner point is the maximum shear stress location, and here what should be the direction of these things? Shear stress direction will be towards this, which is perpendicular to this, let us, this is O and this is B. So, it will be perpendicular to the OB, here also your value will be tau. Similarly, what happens, here also there will be tau value due to this torque, you see comparatively lesser than this, tau value will be comparatively lesser than this corner point value. So, always you should keep it in mind, we should choose that location where our shear stress is maximum, this you should keep it in mind. The resultant shear stress due to, let us, what happens, a welded section, this weld which is subjected to torque as well as it is subjected to two force, here I have shown Px and Pz. Okay. Due to this Py and Pz, let us, this is a weld, it is subjected to a torque mx or torsional moment mx, and there is a direct force Py along y direction and there is another force Pz along z direction. Due to this combining effect, what should be the shear flow along y direction and what should be the shear flow resultant shear flow, you can say, along z direction. These things now I am going to discuss. Okay. So, this I have already shown you. So, you can say shear flow due to along y direction due to direct force Py this you can write as directly, I can write as Py divided by Lw. Always you should keep it in mind, here Lw is the total well length. So, here it is a rectangle. So, here Lw should be 2 into you can say H plus B, because 2 height side and 2 you see breadth side, that is why Lw is this. You can say this is the shear flow due to direct force Py due to Mx. So, by Mx also we are getting a shear stress tau, correct. So, this Mx, this tau already you know, this corresponding to this Mx, tau is equal to what are the things you know? You know this tau you can write as Mx r divided by what? Mx r divided by j. These are the things very well known to you. Now, here you see this tau component we can convert into two component. This tau component here you see, this tau component we can convert into two component. One is q tau y, another will be along z direction, that will be tau let z, you see. So, tau y here and there will be tau z. So, tau can divide into two component, that is very easily you can find out, one is tau y, another one is tau z. So, you see y component will act along y direction and z component will act along, you see what it is called, along z direction. So, corresponding to this tau y, you see what is tau y, directly I am writing here, tau y will be Mx, here thus r, you see tau y will be this perpendicular distance from Cg to that tau y line of action. So, tau y line of action, here generally tau y line of action perpendicular distance is z, let us consider it is z. So, z by j. What is j? J is the total polar moment of inertia of all 4 welds, whatever the 4 side welds are there. So, you can say j is the total polar moment of inertia, you should keep this in mind. Okay. Now, what is now what it is called q y component due to this tau y, this you can write as Mx into z into t, correct, because tau y into t is called q y due to tau y, this throat thickness t divided by j. So, this you can further write as Mx into z divided by j divided by t, that j divided by t is known as Jw, you see Mx z divided by Jw, you should keep this thing in mind. What is Jw? So, this is coming due to Mx along y direction, that is why what is the resultant shear flow along y direction due to Mx and Py. So, Qy resultant which I have written here, Qy resultant, it will be due to this Qy due to this direct force Py, and another component will be Qy due to the shear stress component y, correct. So, these things already I have shown. So, Q this you can write as Py divided by Lw, that means Lw means total well length, plus this Qy due to tau y component is what. So, tau y component you see here, tau y is this direction and this direction is generally you can say tau z. So, we need to take this perpendicular distance. So, here its distance will be along z axis is z. So, that is why you see I have written here it is z. Okay. So, you can write as what, Mx into z divided by what, Jw. What is Jw? Jw already I have told you, Jw is total polar moment of inertia divided by throat thickness t. What is here I am writing, J is equal to total polar moment of inertia and T is equal to throat thickness. Okay. Thickness. So, this idea you got. Now, so Qy resultant you got. So, the Qy resultant here I have shown in equation number 5, you can see. Now, similar way we will get Qz resultant, here you can say this is Qz resultant. So, Qz resultant will be what? So, Qz resultant will be, here I am writing Qz resultant will be due to Pz force, that means here I am writing these things Qz which is due to Pz force, direct force Pz, and there will be Qz which is due to torsional moment Mx. This you should keep it in mind. So, torsional moment Mx, so along z direction what shear stress you are getting, that you can write as tau z here. Okay. So, here that generally this component will be Pz by total well length, okay, plus this Qz will be what? Mx into here what distance we should consider? Here we should consider tau z. So, tau z is the distance from CG of this tau z will be what? This is along y axis, this distance will be y. So, that is why here Mxy divided by Zw. What is Zw? Zw is equal to total polar moment of inertia divided by throat thickness. This you should keep it in mind. Okay. So, this is another component of what it is called shear flow we are getting. This is the shear flow along z direction due to the combined effect of direct force and torsional moment. So, you got the idea how to find out the resultant shear flow in different direction along x, y and z direction. Now, what should be you here one things you should keep it in mind, this whatever the Qz, Qy you are finding out, you need to find out this Qz, Qx or Qy, this you need to find out at maximum stress location point, this you should keep it in mind. Like here we have considered the farthest point which is the corner point in this case, where generally maximum torsional stress is coming, torsional shear stress is coming, you know these things. In case of a you see, in case of a you can say torsional types of moment, if you take a section you know these things, how the shear stress is generally distributing. It is maximum at the outer edge, you see outer edge, and it is generally 0 at centroidal axis or you can say neutral axis you know, and its top side and bottom side generally you see this same types of you can say stress is shear stress is distributing, what I am telling understand. This you should keep it in mind. So, that is why here one things you should keep it in mind, you should choose the furthest distance from the centroid of the, what is this centroid? I have already written here, centroid you need to find out the centroid of all welds, this you should keep it in mind. Okay. So, all weld centroid first we need to find out, after that we need to choose the furthest distance where the shear stress is maximum, that is generally corner point I have already shown. Okay. Now, that corner point and the shear stress always will act perpendicular to the line joining this corner point and CG, I have already shown you. So, this is generally acting at an angle, this shear stress you can divide into two component, one is y direction, another one is z direction. So, due to this y component shear stress, whatever the you see shear flow will be there, that once you need to choose those corner point where that shear stress is adding with you can say with this Qy value. Like here this corner point A you can say is adding with this direct shear force or direct force Px, whatever the Qy you are getting. That is why I have choose this corner point A, or you can choose this corner point B also, if the distance of this distance and this distance A distance and this B distance are same. Here generally this Qy, both the Qy is acting upward direction. So, it is adding together, what I am telling, understand. So, you need to choose those location where you are getting combined effect of this shear flow is maximum. This you should keep it in mind.